Water is the most abundant compound in life, and it makes up about 60 to 95% fresh mass of all living organisms. You and I are made up of mostly water, and I'm sure you have come across the saying, water is life. What this simply means is that water is essential for life. But what makes water essential for life? This is where its unique properties come in. These are that water is polar. It is an excellent solvent. It has a high heat capacity. It has a high latent heat of vaporization. It has cohesive and adhesive properties, and it is less dense as a solid than as a liquid. It is these properties that make water essential for life. And so now let's talk about the individual properties of water. Firstly, we'll talk about water's polar properties. Water is polar, and to understand this, we have to look at the structure of water. The chemical formula of water is H2O, and this simply means that it has two hydrogen atoms bonded to one oxygen atom. The oxygen atom and the hydrogen atoms are covalently bonded, forming water. The bonding that forms the water molecule is depicted in these two images here. As can be seen, there's an interaction between the electrons of the oxygen atom and the electrons of the hydrogen atoms. And as a result of the interaction, water takes up a nonlinear shape, which is this V-shaped structure shown here, known as a tetrahedron. So it takes up this shape as a result of the repulsions taking place at the electron level. If you can see in this diagram, the 6 electrons, the red dots shown in the diagram, 1, 2, 3, 4, 5, 6, belong to the oxygen atom. As we know, oxygen on the periodic table is in group 6, meaning it has 6 electrons in its outer shell. And in order to gain a stable outer shell, it will require 2 electrons, and this is where the covalent bonding comes in. So it will acquire those 2 electrons by forming covalent bonds with the hydrogens. However, since it still has these unpaired electrons, these ones would tend to repel the electrons in the covalent bond, forcing pushing them further, pushing the covalent bonds further from the unpaired electrons. This forms this V-shaped structure we see, the tetrahedron. So when this repulsion takes place, the angle between the hydrogen bonds in the water molecule is reduced to 104 degrees Celsius. And this is the angle that we see being shown in this diagram here. So you have the oxygen atom there, you have the hydrogens covalently bonded to each other. And then due to repulsions by the unpaired electrons on the oxygen atom and the covalently bonded electrons, you have this structure forming with the angle between the hydrogens being 104.5 degrees. Of importance to the structure of water is oxygen's electronegativity. What this simply means is that when the oxygen is covalently bonded to the hydrogen, it will have the tendency to pull the electrons in the covalent bond towards itself in such a way that you have a group of electrons around, you have the bulk of electrons around the oxygen atom, and then the hydrogens quite right covalently bonded to the oxygen, but however, the electrons are further away from the hydrogens and more close to the oxygen. So as a result of this, what will develop is that you have you have partial negative charges on the oxygen and you have partial positive charges on the hydrogen. So on the oxygen, because it's bonded to the two hydrogen atoms, you have a partial charge on this one side, and then you have a partial charge on this other side here, and then you have a partial positive charge on this hydrogen and a partial positive charge on this hydrogen. These partial charges that form on water are responsible for the polarity of water. And this polarity of water means that the oxygen and the hydrogen atoms in the water molecule are capable of interaction with other compounds. And these compounds are through hydrogen bonding. This hydrogen bonding is responsible for all the other properties of water. So let's take a look at how this happens. When you look at the diagrams here, you see the water molecules interacting via hydrogen bonding. This is what is shown here. So you have this hydrogen interacting with the oxygen of the other water molecule, forming a hydrogen bond. If we look at the next slide here, you have it showing you the same hydrogen bonding. This time we were able to see the partial positive charges of the water molecules. So it's because of these partial charges, the hydrogen here, which has a partial positive charge, will be able to interact with the oxygen that has a partial negative charge. So this interaction will be occurring between various water molecules, as you can see in this diagram. This diagram here is trying to illustrate what is known as aphoterism. This simply means that the water molecule can, due to the lone pair of electrons on the oxygen, it is able to accept a hydrogen atom from a neighboring water molecule. So this hydrogen atom could bond to this water molecule, and this would make this water molecule here acidic, whereas this one here would become basic. So water can act both as a base and as an acid. It can act as a base by accepting the hydrogen atom, whereas this one here, this water molecule, which is donating the hydrogen atom, is acting as an acid. That is what is referred to, what is meant when they say water is aphoteric. So far, we've looked at the structure of water and how it comes about due to the repulsions. We've also looked at the polarity of water that comes about as a result of oxygen being more electronegative than the hydrogens, thereby drawing more electrons towards it, giving the hydrogens and the oxygen partial charges. And then we've seen how these partial charges eventually lead to hydrogen bonding of the water molecules. Now we'll go on to see how this hydrogen bonding will further lead to other properties of water. So let's look at water as a solvent. You have probably come across the statement, water is a universal solvent. This is not entirely true, as we will see. Water is only able to interact with other polar substances, and this is what these images here are trying to depict. So, for example, sodium chloride, which is an ionic compound. It's so you have the sodium and the chloride in the sodium chloride having charges. You have the sodium having a positive charge and the chloride having a negative charge. When you place this in water, you have the sodium atom interacting with the negatively charged oxygen atom of the water, and then you have the chloride interacting with the partially positive hydrogen atoms of the water. From the interactions due to water's polarity, water's solvent properties are also mainly due to the very small size of the water molecule. So if we can look at this image in the middle here, you have a sodium atom that is interacting with a number of water molecules due to the size. So due to the size, these water molecules are able to surround other compounds effectively. And that is also what gives rise to water being a very good solvent. However, what happens when a non-polar substance is placed in water? If you look at this next slide, say for example, you have fats, a phospholipid, which is basically made up of fats, which are non-polar. So if these substances are placed in water, fats, as you know, they'll have a portion of their structure which is polar and able to interact with water. Then you have a portion of their structure which is unable to interact with, which is non-polar. So if you look at the images here, you have these blue structures here which are able to interact with water. And then you have these other structures here which don't have any charges and thus are non-polar and are unable to interact with either the oxygen or the hydrogen in the water. So what this simply means is that when you place this substance in water, you have the blue portions there interacting with water, and you have the yellow portions here unable to interact with water. And as a result of this, what you have is what are known as micelles. So these are structures where you have the portions able to interact with water on the outside, and you have the portions unable to interact with water on the inside. These portions able to interact with water in the cases of fats would be referred to as being hydrophilic, that is water loving. And these portions which are unable to interact with water would be considered hydrophobic, scared of water, water hating. Let's now look at the other properties of water, which are it having a high heat capacity and it having a high latent heat of vaporization. Uh, these properties come about as a result of the hydrogen bonding, as earlier mentioned. So heat capacity is simply the amount of energy required to raise the temperature of 1 kg of water by 1 degree Celsius, whereas heat of vaporization is the amount of energy that is required to vaporize the liquid. So in the case of water, this is the amount of energy required to change water from its liquid form to its vapor form, which is steam. So water has a high heat capacity due to the fact that when energy is applied to the water molecule, that energy is first used to weaken the bonds between the water molecules before it can increase the temperature of the water in general. Whereas it will have a high latent heat of vaporization due to the hydrogen bonding as well. When water is being heated up, those hydrogen bonds have to be broken before it can turn into steam. And those hydrogen bonds require a lot of energy to be broken up. And this is what gives water its high latent heat of vaporization. This brings us to the other properties of water, which are that it has cohesive and adhesive properties. What cohesive simply means is that the water molecules stick together, and this sticking together between one water molecule and the other water molecule, as has been explained in this tutorial over and over, is due to the hydrogen bonding. So if you can look at this image where the pointer is, you have this water molecule interacting with that water molecule via hydrogen bonding. Then you have this water molecule interacting with this one here via hydrogen bonding, and so on. So all these water molecules here are sticking together by hydrogen bonding, and that is what is referred to as having cohesive properties. Adhesive properties simply means that the water molecule, instead of the water molecule is shown, if we can go back, due to its polarity, you can have hydrogen bonding forming between the water molecule and another compound. And that's what brings about its adhesive properties. So you have hydrogen bonding between the water molecules and the other compounds. And these cohesive and adhesive properties of water are what are responsible for the surface tension, the water's high surface tension, and also its capillarity action. If you look at this diagram again, so you have these water molecules at the top, which are interacting via hydrogen bonding with the water molecules below them. But then here at the surface, because above the water molecules, you have air molecules, and water molecules are more likely to interact with other water molecules than with air molecules. As a result, you have the water molecules at the top forming stronger hydrogen bonds, and this will create a sort of a skin up there, some sort of skin, and this skin is able to resist external forces. This resistance to external forces is what is known as surface tension. So if you apply a force here, these water molecules will be will resist, they won't break. And that resistance is what is referred to as water's high surface tension. Now, if you look at this image here, you have this insect, water strider. So this water strider is able to perfectly balance its body mass in such a way that it walks on water. This walking is due to the skin formed on the surface of the water due to this surface tension. And thus you have that water strider walking on the water. If you look at this image here, so you have a plant leaf here, and then there's a water juice. Simply you in the morning when it's cold and so on, you see water droplets forming on the leaves. So you have the water molecules in this droplet. So they'll form this bubble due to the fact that there's the surface tension up there, and then the hydrogen bonding there on the water molecules at the surface there. The hydrogen bonding will be stronger, and that will force it into this bubble shape. Then you have the water molecule still attached to the leaf in that way, resisting forces of gravity and so on. So this also demonstrates water's high surface tension. One other thing that develops as a result of the cohesive and adhesive properties of water is water's capillary action, where you have if you had a narrow tube, example would be in plants where you have xylem cells, which are just tubes of sorts. So you have that water molecule moving through this narrow tube by means of capillarity. And how it does this is that once one water molecule is drawn in, it will, since it's bonded to another water molecule via hydrogen bonding, it will pull that other water molecule with it. And then you have that upward flow of the water in the narrow tube. And that is what is known as water's capillary action. The same can be seen if you were to say put water in a beaker. So you would have the water molecules sticking together by cohesion, and then you would have them sticking to the walls of the beaker by adhesion. And then as a result of the cohesive and adhesive properties, you would have that meniscus forming. This brings us to our last property for this discussion, which is that water is less dense as a solid. The change in density of water from its density as a liquid to its density as a solid can be attributed to the change in the water structure. This change occurs at a temperature of 4 degrees Celsius. So above 4 degrees Celsius, you have the water molecules having this sort of arrangement where they're interacting with each other via hydrogen bonding. And at 4 degrees Celsius, you have the water molecules. These water molecules will form the maximum number of bonds they can form, which is 4. That will give it this structure shown here. This structure right here. Which is known as a crystal lattice structure. And this is the structure which ice will take up. So you have one water molecule interacting with 1, 2, 3, 4. Let's see if we can see a clear one. So we have, say, this one here. It's interacting with this water molecule here, this water molecule there, this water molecule there, and this one here, forming a maximum of 4 bonds. This interaction will give water sort of a linear structure, which creates more space between the atoms. And because of this, the change in the configuration of the shape, the more space in between the atoms, ice tends to be less dense than its liquid form. Water tends to be less dense as a solid than as a liquid. So on this slide, what we have are some revision questions. The first one says, draw 3 water molecules interacting via hydrogen bonding, showing the partial positive and partial negative charges. We covered this in our discussion, and if you look at this diagram is showing the water molecules interacting via hydrogen bonding with the partial charges shown on the diagram. Question 2 says, describe 3 different properties of water that make it very important for life. That is what we've been doing throughout our discussion in this tutorial. So you can just watch the video, and you should be able to describe at least 3 properties that we've discussed. Actually, you should be able to describe all the properties that we've discussed. Question 3 says, explain the amphoteric properties of water. The amphoteric properties, as was mentioned in this slide here, this is where water will be able to act as a base or as an acid, where it's able to accept a hydrogen atom from a neighboring water molecule or from another compound, which could be an acid. So the water molecule could accept a hydrogen atom from the acid. And then apart from this interaction, the water molecule can also act as an acid, where it can act as an acid, where it can donate, or like in the example that we had earlier given. If you look at this water molecule accepting a hydrogen atom from this other water molecule. So in this instance, you would have this water molecule acting as a base, and you'd have this water molecule acting as an acid. The same interaction can happen between a water molecule and another compound, which is a base. So that base could accept a hydrogen atom from the water molecule. In this case, the water molecule is donating the hydrogen atom to the base, and this is what is referred to as water's amphoteric properties. Question 4 says, suggest how you test the high surface tension of water using plants. This is what we're explaining with the water bubble. The water bubble the water bubble is the dewdrops that form on leaves of plant. And we explained in the tutorial that these water bubbles will form due to the surface tension, and they'll be there adherent to the water leaf, resisting the forces of gravity. And as such, using this, you can explain how water has a high surface tension. Question 5 says, why are the temperature ranges of water in which it remains a liquid important for living organisms? So what this question is simply asking you to explain is water's high heat capacity. So the heat capacity, which is the energy you require to raise the temperature of 1 kg of water by 1 degree Celsius. So you require a lot more energy to raise the temperature of water due to the fact that the water molecules are interacting via hydrogen bonding. And when you apply that energy to the water molecules, that energy will first be used to weaken the hydrogen bonds before the overall temperature of the water can increase. So what this simply means to living organisms is that you, in the instance of aquatic life, you could have the top half of, say, you could have the top side of a water body having a colder temperature, whereas at the bottom you have it having a higher temperature. So when you look at question 5, why are the temperature ranges of water in which it remains a liquid important for living organisms? What this question is simply asking you to explain water's high heat capacity. And we had discussed this on the slide where we talked about the heat capacity being the energy required to raise the temperature of 1 kg of water by a degree Celsius. And this energy is high due to the fact that when the energy is applied to the water, it's first used to weaken the hydrogen bonding in the water molecules. And what this simply means is that there will be very little fluctuation in the temperature of water. And for living organisms, as earlier mentioned, now most living organisms, water will make up about 60 to 95% of fresh mass of living organisms. So you have most of the cells of living organisms in an aqueous solution of sorts that is surrounded by water, and you have most biochemical reactions in living organisms occurring in water, and this happen within a narrow temperature range due to the fact that there's less fluctuation of water, less fluctuation in temperatures of water. That brings us to the end of our discussion on water. Thank you very much, and hopefully it has been helpful. In this discussion, we've talked about the properties of water, which make it essential for life. We explained on its structure and the hydrogen bonding, and we've covered some questions. We've covered the questions, the revision questions. Thank you very much.